Hi everybody, welcome to the shop. I'm Jarrell with Jarrell Education. Today, this first video is starting a series on Newton's laws, and we're talking about forces and things like that, but now we're going to involve some calculus, and we need some differential equations to do it. So this is the first video in a series, okay? This video is going to be kind of long, and there's three parts to this video because there's three relevant types of differential equations that you need to be able to solve. This is by no means an extensive, exhaustive treatise on solving differential equations. That is way outside the scope of this video. This is just showing you the ones that you need to be able to go through, okay? So some basic calculus in this. Now, what I suggest is when you're going through this first video, there's going to be a bunch of them in the series. I can't do it all at once. It would be like 2 hours long. So when you're going through this first video, I would say look at the example, pause the video, try to do it, and then maybe watch the solutions in double time because we're getting on towards 15, 20 minutes. I think that this video will be when I'm done. All right, let's get started. Let's get into it. And as always, if my content helps you and you like it, please subscribe, leave me some comments so I know that I'm doing the right thing. Okay, let's get into it. Looking at differential equations. That's the topic that we're getting into. All right. So now typically in math, you're used to seeing equations that are things like 2x plus 5 is equal to, I don't know, 13 or something like that. And then you solve that, you subtract 5 from both sides and you get 2x is equal to 8. And then you divide both sides by 2 and you get x is equal to 4. And even when the equations get fairly complicated, like e to the x plus 5 sine squared of x minus 7 is equal to 19 cosine of x. Okay? These are still equations that are, I guess for lack of a better word, we'll call them static. Maybe they have an answer, maybe they don't, but if you can't solve it, by hand with pencil and paper, you plug the thing into a calculator, and then you look at where the two graphs intersect each other, and then you find the points that way. Okay? But when you think about it, okay, it would make if you're a scientist trying to relate two quantities together, it might be more complicated than just relating like static variables together. What you might be doing is not only are they related by the variable, but they could also be related by how quickly they're changing. Okay, and this is where differential equations comes in. So let's start with what we need. All right, so let's say we have this equation, dy dx, all right, is equal to 2x. Okay, now if that's all we're given, there's only so much we can do with this. Basically what this says is, all right, the rate of change of y with respect to x turns out to be 2x. Now how do we solve it? Well, I think it's, you can almost, if you've had any calculus at all, you can look at this and basically say, oh, I know the answer is y is equal to x squared plus some constant. Okay, but let's look at it as if we can't just see that. So I have dy dx is equal to 2x. All right, now there's a reason why we write the notation for the derivative as a fraction. Now I'm going to say this, dy dx is technically not a fraction, but here's might be the controversial part. If you use it like a fraction, you're always going to be right. Okay, so that's a good way to think about it. So when I'm solving this differential equation, the first thing we do, and this is really all we're going to cover in this little mini differential equations lesson, is called separation of variables. All right. Now the way you solve this is basically you get anything with an x or a dx on one side and anything with a y or a dy on the other side, and other variables as appropriate. So what I'm basically going to do is I'm going to rewrite this by saying dy is equal to 2x. What I then do is I integrate both sides. Okay, and then I literally just look at this side and say, what's, think that's really a 1 there. So what did I differentiate with respect to y? Do you have gotten a 1? Well, that must be a y. Okay, and then it's equal to, well, what did I differentiate over here to have gotten a 2x? Well, that must have been x squared. Now you might argue like, okay, well, I got to write like a constant here, and I got to write a constant there, c2, different constant. Or what you could say is just like, instead of doing that, whatever the constant that went with y was, I'll just add it to both sides or subtract it from both sides and then write it over there with x. So typically we do it that way. So that's y is equal to x squared plus a constant. Okay, so this would be what's called the general solution to that differential equation. Now, sometimes you'll be given this. Let's do the same thing. You'll be given dy dx is equal to 2x, okay? But then they'll give you some sort of initial condition. They'll say something like y of 3 is equal to 11. So then we basically do the same thing. We say, okay, let's separate our variables. Dy is equal to 2x dx, and then let's integrate both sides. And now I have y is equal to x squared plus a constant. And then that's where this comes in, okay? Now this solution up here is called a general solution. So there's no initial condition given, and that's just the best I can do. Now when I have this kind of thing here, this is going to be a particular solution. So basically now I say, okay, well, here's the general solution, and now I'm going to actually take the extra information that I have. That's an 11. I'm going to take the extra information that I have, and I'm going to figure out exactly what c would be, that constant that I had on there. So if I let x be 3, y would be 11. That's what that says. So I'm going to put 11 in here, and then this is equal to 3 squared, because I'm letting x be 3 plus a constant. So that means 11 would be equal to 9 plus c. So that makes c equal to 2. So for this differential equation with this initial condition, I would say that my particular solution would be y is equal to x squared plus 2. Okay, now you might say on that last example, you didn't really need any differential equations to solve that thing. You know, you could have just looked at it and sort of figured it out. And you wouldn't be wrong. Okay, but okay, like I said before, don't think that you don't need differential equations. It's a serious subject. Okay, now we're going to do an example now that's a little bit more difficult than that. So first thing I want to say though, before we do that, I need you to understand this. Like, I'm just going to pick a random number, so 5, and let's say I wrote 5 to the x plus 2. All right. Before I get started on this next problem, I need you to understand that this is the same thing as 5 to the x times 5 to the 2, which would really be the same thing as 25 times 5 to the x. Okay? And remember, you can't just multiply the 25 by the 5 because exponentiation comes before multiplication. All right, so I'm going to use that fact in a minute. All right, so I just wanted to say that, get that out of the way so that you're prepared for it when it comes. So here we go. So now what we're going to solve is we're going to solve the differential equations dy dx is equal to -2 times y. All right. Now, first of all, this is a little bit different because we're trying to figure out a function of x like we did in the last one, right? Remember, our answer was a function of x. In fact, what was it? It was x squared plus 2. This was our answer. So the solution to a differential equation is not necessarily a number, right? It's actually a function that we're looking for. So here's the thing. Now we have dy dx is equal to -2 times y. And y is a function of x. So what we're looking for is the function of x. Now let's go do this just like we did before. Let's separate the variables. dy is equal to -2 times y times dx. I multiplied both sides by dx. Now remember what I said. We got to get the y's and dy's on one side and the x's and dx's on the other side. So I've got 1 over y dy is equal to -2 dx. And now I'm going to integrate both sides. And now I have the integral of 1 over y dy is really just the natural log of the absolute value of y. Now I'm going to do a video later on why that is the absolute value of y, okay? But for now, just accept it. I don't want to get too bogged down in too many details. Then over here, this is going to be -2x plus a constant, right? In other words, you're thinking of it like, okay, well, if the function that I took the derivative of was -2, well, the function must have been -2x. All right, it must have been linear because I'm getting a constant for the derivative. All right, so I have this. Now, I haven't really solved for y yet because y is still stuck inside a natural log. So what I'm going to do is I'm going to make this, the left, the exponent of e, and I'm going to make the right an exponent of e. So now on the left, I have e to the natural log of y, absolute value, is equal to e to the -2x plus c. So this is just y, because e to the and natural log of undo each other, so it's just y. And then this is going to be equal to, like I said before with the little example I showed you in the beginning, this is equal to e to the -2x times e to the c. But remember, c is a constant, and e to the c is also going to be a constant. So what I have is this is going to be y is equal to e to the c times e to the negative 2x. Now, a lot of times what people will do is instead of writing e to the c, they'll just write that as this. They'll say y is equal to some constant a, right? Because e to the c is a constant. It just looks more complicated, times e to the negative 2x. Okay, so here would be my general solution. Now let's scroll back up to for a second. This was my original problem right here. Now I didn't give you any initial conditions, but let's suppose now that I did. So what I just did is I found this was the general solution to that. Now, if I had said to you, okay, my initial conditions for this differential equation were that y of 0 is equal to 10. Now that I found the general solution, now I'm going to go back and say, okay, now I want a more particular solution. Let's see what we actually have when I put that on it, right? So now I'm going to rewrite that up here. If y is equal to a times e to the negative 2x, that's my function right there. Okay, that's what I found. And this is my initial condition. All that says is like, all right, put a 0 in for x. So I'm going to get 10 is equal to a times e to the negative 2 times 0. Now that makes this whole thing e to the 0, which is just 1. So that means a would be 10. So my particular solution in this case would be y is equal to 10 e to the negative 2x. And there it is. Okay, we're coming down the home stretch, and now we're about to do a differential equation that's going to be very relevant for us when we drop a ball and we consider air resistance. So we're looking at the drag force, all right? Now, before I actually get into that differential equation, I got to do one prerequisite to make sure that you're okay with this so it doesn't look weird when I do it right in the middle of a problem. So imagine I have this. I have 5 minus 3x, okay? And what I want to do is I want to write that as like x minus some number, maybe in parentheses or something. Now what I'm going to do then is in this case, I'm going to factor a negative 3 out. So I'm going to pull a negative 3 out of both terms. Now if I pull the negative 3 out of 5, that means this is going to become negative 5/3. Because when I multiply the 3 back in, the negative 3, I have to get 5, okay? And then plus x. And then when I write this turned around with the x coefficient first, this is going to become negative 3 on the outside, and then it's going to be x minus 5/3. 5/3, okay? So, that's going to come up in a minute. In fact, what I'm going to use is, let's do that right now. All right, so imagine I have, let's put this in here. I have 4 minus 2y. But I want to write that with the y with no coefficient other than 1 on it, and I want to make it positive. So that means I'm going to factor out a negative 2. Okay, so if I do that now, that's going to become negative 2 is on the outside, right? Now to get a 4, when I multiply that back in, this would have to be negative 2. Okay, and then it's going to be plus y. And you can check if I multiply that back through, I'm going to get 4 minus 2y. All right, negative 2 times negative 2 is 4. Negative 2 times positive y is going to be minus 2y, and I get back what I had. Okay, but I just needed to look like that. All right, that being said, hopefully that helped. I got dy dx is going to be equal to 4 minus 2y. I want to solve this differential equation. All right, so we're going to do the same thing that we always do. Multiply both sides by dx. So I have dy is equal to 4 minus 2y times dx. Now notice I'm not distributing the dx into both of them because then it would become impossible to separate it, okay? All I'm going to do is I'm going to divide both sides by 4 minus 2y. So now I get this. I get 1 over 4 minus 2y dy is equal to plain old dx. Okay? I should note, I'm going to put initial condition on this. I'm going to let y of 0 be equal to 0. But anyway, that doesn't change anything that I've done so far. Okay, now I'm ready to integrate. I've got all my y's and dy's over here on the left, right? There's nothing over there, no x's over there, and I've got all my x's and dx's over on that side. So now when I integrate both sides, I'm going to integrate the left, I'm going to integrate the right. Before I start doing this, it's going to make it a lot easier if I do that little trick I showed you. So watch what I do. I'm going to take the integral, right? 1 over. Now, out of this bottom, I'm going to factor out a negative 2. So that's going to become negative 2. And then on the inside, I'm going to be left with negative 2 plus y, just like I showed you before. And you can notice if I multiply that negative 2 back in on the denominator, it's going to become positive 4. And then if I multiply that back in, it's going to become negative 2y. Okay? And I have dy, and that's equal to the integral of dx. Remember, there's just a 1 there. Let's scroll up a little bit. All right, so now I'm going to pull that negative 2 on the denominator and pull that out. So this is going to be negative 1/2, okay? And then I have the integral of 1 over y minus 2 dy is equal to the integral of just 1 dx. And now, just to make it a little bit cleaner before I do it, I'm going to multiply both sides of the equation by negative 2 so that I can get rid of that negative 1/2, right? So then this on the left is going to become the integral of 1 over y minus 2 dy, and that's going to be equal to negative 2 integral dx. Okay, now I'm ready to go. So now that I cleaned it up a little bit, the integral is not going to be as awful when I do it. So this is going to be the natural log of the absolute value of y minus 2, and that's going to be equal to negative 2x plus a constant, because the integral of 1 is just x and the negative 2 is riding along. Now, like I did before, I'm going to make I'm going to make both sides. I'm going to make this an exponent in e, and I'm going to make this an exponent in e. Now let's kind of scroll up over here, right, and continue the problem over here. So now I have e to the natural log of y minus 2 is just going to be y minus 2. So I'm going to have y minus 2 on the left, right? And if I look back here, it's going to be equal to e to the negative 2x plus c. Do that little trick that I had before. This is going to be y minus 2 is equal to e to the negative 2x times e to the c. But don't forget, this is just a constant, so I'm going to call it one name in a minute. So this is the same thing as y minus 2 is equal to a times e to the negative 2x. Then I'm going to add 2 to both sides. So y is actually going to be equal to a e to the negative 2x plus 2. And this would be my general solution, okay? But let's not forget, all right, I have that initial condition. So I'm going to let y be 0 when x is 0, and then I'm going to see what that constant a actually is. So I get 0 is equal to a times e. Now when I plug in a 0 for x there, that whole exponent's going to become 0, so that's just e to the 0 plus 2. And that means, right, 0 is equal to a plus 2, which means a is actually going to be negative 2. So when I pop that into my function here, I'm going to have y is equal to negative 2 e to the negative 2x plus 2. Okay, and I can write that as y is equal to, I'm going to factor out a 2 times 1 minus e to the negative 2x. And there's my particular solution.